to be back here and actually with the physical book in hand. You know how long it can take if you've been working on one of those. Statistical inference as severe testing, how to get beyond the statistics wars. Okay. I couldn't resist making use of the title of this series of talks in my own title. And of course, the term severity is really Popper's, so how perfect. But the whole idea of having a method that with high probability would have refuted a claim if false was too much like having a reliable method for Popper to accept, thinking that it would give him that whiff of induction that he was trying to avoid. So my idea is that we can use some of the contemporary techniques in statistics to make good on this notion and also on Popper's idea of corroboration. However, statistics itself has quite a lot of controversy in its own right. Some years ago, David Cox declared that, you know, in a lot of fields, foundations don't seem so important, but we both think that foundations of statistics are important, and why do you think that? And I said, well, in statistics we invariably cross over into philosophical questions about induction and knowledge and learning. And so it's really by tackling both sets of problems at once, philosophical, inductive problems, and the statistical one, that we can get around them. David Cox was supposed to be here today. He called me as he said he had just been making it to the train station and decided he was getting too dizzy. I think he's 96 this July, so he went back. And what you might wonder why I'm being asked questions by Cox, and actually it started out as me interviewing Cox, but he didn't think I was doing it right, so he said, I'll show you how to do it. And he started asking me questions, and the whole interview went on that way. Okay. So a central role in these statistics wars, a central problem has to do with the role of probability. Should probability be used in order to ensure that we won't too often erroneously interpret data in some sort of long-run use, or to capture degrees of belief, confirmation, and support? So the disagreements between competing tribes of frequentists and Bayesians have been so controversial that many people, all of us want to believe, we're really long past them. But the truth is, these debates and these disagreements come up, especially in today's problems of irreplication and issues of restoring the integrity of science. It's thought, well, you know, maybe today we have agreement. We don't have these warring tribes. We have unification. And besides, people are very eclectic, prepared to use whatever method works. But in fact, these long-standing battles still simmer below the surface. It's not enough to have an agreement on numbers when they're measuring different things. You've got to a kind of statistical schizophrenia. So I say in this book that we should brush the dust off the pivotal debates, but in relation to today's statistical issues. So what are these issues? Why are we constantly hearing that science is in crisis? And it really has to do, very simply, with the fact that it's become too easy to come up with impressive-looking findings, even though they are spurious. And so I set sail with a very simple tool, a kind of minimal requirement for evidence. If nothing has been done to find flaws in a claim, okay, then you don't have evidence for it. It certainly hasn't been severely or stringently tested in the least. And I think that we can all agree with this, and the idea here is that probability would arise in order to capture the probative capacity of tools, how good a job was done by a certain method in uncovering errors if they exist. So that's a different role for probability. I don't mean in putting forth this idea that we're always going to be doing formal tests. It's sufficiently general to apply to any method now in use and is also applicable to prediction, explanation, and estimation. Furthermore, you don't have to accept this philosophy to use it to understand and get beyond the statistics wars. I see it as a tool for excavation and for getting us beyond some of the marshes and quicksand of today's debate. So I call this a philosophical excursion. I even suggest you should see it as one of these special interest cruises. And I have tours. I don't have chapters. I have tours and excursions. And in so doing, we enter into museums and engage with a host of tribes and see how they have clashed, see their peace treaties and shifting alliances. And that ship is in the book, actually. That's the Cambridge University ship. Okay, so feel free to stop me and ask a question as I go. Okay. Well, unsurprisingly, the most often used tools are the most criticized, namely statistical significance tests. And this is John Ioannidis saying that the problem of non-replication is a consequence of claiming conclusive research findings on the basis of a single statistically significant result at some arbitrary level, like 0.05. Do people really do that just on the basis of one? It would be a genuine and very dramatic violation of the core requirements for simple significance tests put forward by R.A. Fisher, who said, we're not interested in an isolated small p-value, but a reliable method of procedure. And we're only allowed to say that we've demonstrated a phenomenon when we know how to bring about results that would rarely fail to give us a statistically significant result. Okay. So what is a significance test, a simple significance test built on p-values? The idea here is we're trying to test the conformity or agreement of data with some reference hypothesis or null hypothesis H0, and we find a function t, it's a function of the data, such that the bigger t is, the more discrepant the data are from what you would expect under H0. Okay. Furthermore, we have to be able to compute this probability, called the p-value, the probability of getting a difference as large or larger under the assumption of H0. We know there's expected variability, so if there's a high probability you get an even bigger difference than you observe under the assumption of chance variability, then you don't have evidence of incompatibility. Okay. If you have a small p-value, it does indicate some underlying discrepancy from H0 because very probably you would have seen a less impressive, a smaller t-value, okay, if in fact H0 were true. But even if you have that small p-value, it's not evidence of a genuine statistical effect, which we can write as H1, let alone jumping to another level, to H star. And of course, this is a well-known fallacy to go from statistical to substantive. And that's what Ioannidis is saying people do. This is just a blatant fallacy. I call it the fallacy of projection, because H star makes claims that haven't been probed at all by our statistical tests, or at least it's fallacious when that is the case. The whole question about moving from experimental interventions and statistical claims to substantive claims really don't get enough attention in today's replication crisis. But at least your tool should block going immediately to them. So Fisher may have told us not to do it, but didn't officially block it. The Neyman-Pearson test that came along to improve on Fisher's test do. Here we have not just a null or reference hypothesis, but also an alternative. An example might be that the null says there's no effect, or the effect is less than 0, versus there's some. So when you reject, if you do find evidence against that null, the most you're going to do is infer that alternative. And the null and the alternative have to exhaust the space, the whole parameter space. So at least this move of sort of jumping levels would be blocked. Okay. And by introducing this alternative, we also have the second type of error, failing to reject the null when you should, the type 2 error, and the corresponding notion of power.
Deborah, just on the question of what you can infer from a single test, should we distinguish two cases? One where the p-value is, say, below, for example, 0.05, but not very much below, in which case you say it might just be down to chance, the sort of thing that David Colquhoun has written about. And different cases where you might have a single test, you get a p-value of, say, 10 to the minus 9, and in that case you would say it's not down to chance, but of course it may be down to something wrong with the way the experiment is done. That's always a possibility in it.
You're asking whether we should make a difference between the actual the value attained. I mean, I definitely do. I'm opposed to this idea that we have a strict cutoff. And the way that I reinterpret tests, because I admit they do need reinterpretation, is by looking at the actual outcome and figuring out what discrepancy, parametric discrepancy, you have good evidence for. And the much smaller the p-value will be evidence for a larger discrepancy from the null than the smaller one. That's how I take account. Does that answer? I'm not sure. But of course, if you have such a large sample size, it may be that in fact the difference that you have detected is not substantively interesting because it may be too small. So we often hear that Fisher's methods are very different from Neyman-Pearson methods, but they both agree on a central thing, that it's easy to lie with statistics with sufficient finagling, or as I call biasing selection effect, cherry picking, significance seeking, multiple testing, looking for post-data subgroups, trying and trying again, because these techniques may practically guarantee a preferred claim gets support, even if it's unwarranted. So this counters this severity requirement, this minimal principle that I said we would set sail on. If the tests have little or no capability of finding flaws, even if they're there, then finding an agreement between the data and that claim is not good evidence. It provides poor or maybe even no evidence. Okay, that's the severity requirement. And the idea about seeing statistics as severe testing is to try on this idea that that's the role of probability, instead of the two that we most often associate. So I call the first probabilism, and that is the idea that probability will be used to capture degrees of probability confirmation and so on. It could be absolute or comparative. I'm going to put them all under that rubric, including likelihood ratios. The performance idea is that probability arises to ensure long-run reliability, coverage probability, and so on. Okay. This third idea is needed because neither probabilism nor performance really captures this idea of error-probing capacity. Good long-run performance is at most unnecessary, but not a sufficient condition for a severe test. And this is also the key to solving a central problem for frequent tests who are always put on the defensive. If all you can say is your methods have good long-run performance, then what is it telling me about the case at hand? Okay. And here, the answer is that it's telling me whether I have a severe test. Ask yourself what bothers you with the p-hacker, the cherry picker, selective reporting. It's really not that this is a method that would often give us false hypothesis in some long run, even though it's true, even though it is an unreliable method. What we say, and what bothers us, is that they haven't done a good job in the case at hand. It hasn't done a good job of avoiding known errors in interpreting data. So my idea is that the performance is relevant when it teaches us about the capabilities of our method. And that's really the justification for at least the special context, limited that it may be, for using frequentist statistics in science. So to compare the three ideas in terms of when a claim is not warranted, for the probabilist, unless the claim is true or probable or gets a probability boost made comparatively firmer. And the performance idea is not warranted unless it stems from a method with low long-run error. And I'm proposing this idea. We can give it another P, so they're all P's. Probativism. It's not warranted unless something, ideally a fair amount, has been done to probe ways that we can be wrong. Okay. So let me give you a couple of examples. One is informal. These are examples that are mindful of London, because whenever I come here, I tend to gain weight, and I test using a series of well-calibrated scales both before leaving and return. And usually my clothes are enough to indicate it, but say that of all of these scales show an over 4-pound gain, whereas none of them show any difference with respect to a book or other object of known weight, like my error in the growth is exactly 1 pound. So I know the scales are working, then I have to infer I gained at least 4 pounds, totally informally. When you think about the properties of the weighing methods, that is akin to the performance properties, how well does the scale perform. But nobody would claim that the justification for my inferring the 4-pound weight gain is merely that if I do this, I'll often be right in the long run, but I can't say anything about my weight right now. No, we would argue that the source of the readings, the properties of the tools, let me say something about the source, namely my weight. So this is the philosophical idea behind this account. Of course, I could always say that the scales are wrong. They work fine in weighing objects with known weight. They just trick me. There's a conspiracy of the scales when it comes to something of unknown weight. There's this extra assumption. I say the severe tester is in a very special context. We're not always in that, or even often in the context, of wanting to find things out. And that's why I don't just dismiss those and say that too extraordinary a circumstance for all the scales to go astray. So I make this inference about my weight. Yeah? Okay. Now, I introduced statistics in this book with a section called Statistical Inference and Sexy Science, because some people have said to me, when I talk about maybe general relativity or I have a discussion of Higgs, that I'm talking about something very different from what they're involved in down in the dregs of statistics. I'm talking about highfalutin sexy science. So I want to emphasize that even large-scale theories connect with data only through intermediate hypotheses and models from the data generation. And this is a very crude set of pigeonholes. It's just that you can never find one, if you try, that's going to work for all cases. So I decided after many years of trying that I would just have these pigeonholes, and as long as I can have them grow as needed, that would be a way to distinguish the different levels. And severity would apply actually on all of them, and with background information all around. Okay, so I couldn't resist, because the last week, on May 29th, it was 100 years. I didn't see any big celebrations as a result, but anyway, 100 years from testing general relativity based on the eclipse effect, because on Einstein's theory, you would expect light deflection, so a star would seem to be deflected slightly, but it's a very small amount. And that small amount would be for light just grazing the sun, and actually we can only detect things that are at least one solar arc away. But it just so happened that a total eclipse of the sun, by strange good fortune, would occur on these dates. And so 2 expeditions would be mounted, and they were going to ask 2 questions. First, is there a deflection effect of the amount predicted by Einstein as opposed to Newton? And the Einstein amount was 1.75, and the Newton is half that. Secondly, its cause. Is it attributable to the sun's gravitational field, okay, as described by Einstein? And so they went to Sobel and Hippie in order to get these eclipse photos, and then they could use a statistical method that was very familiar to them from stellar parallax to compare that eclipse plate to the positions of the same stars 6 months before at night when the sun is absent, and get an estimate. Okay, so that first problem about whether there's a real effect is reduced to a statistical one. That the observed mean deflections are normally distributed around the predicted mean, which they do the test in terms of the Newton prediction. One-sided test could be. And the alternative, notice, includes the Einsteinian value that you could then estimate. So these 2 expeditions set out. After about a year it took to check the instruments and so on, these are the results. I'm giving them here in terms of standard errors. They actually gave them in terms of probable errors. And Eddington says it's usual to allow a margin of safety of about twice the probable error on either side of the mean. That's actually only 1.4 standard errors. That's not so much. And using this, the Principi plates, he says, are just sufficient to rule out the Newtonian half deflection, and the Sobel plates, he thought, really falsified the Newtonian value completely. Then moving on to the second stage. But is it, we have an effect, okay, we have some evidence of it, but is it attributable to the sun's gravitational field? At this point, it was entirely legitimate to use the known eclipse effect to come up with explanations, including explanations that would save Newton from falsification, because this was a known effect. Moreover, any conjecture explanation was going to be hit with a very severe test. So there are numerous examples, and the literature is really interesting. One example is from Sir Oliver Lodge, who actually said he pre-specified, okay, his effects, and he said that if the Einstein effect seems to be credible, I'm going to come up with these Newtonian explanations. And there are quite a few. Because, and this is Harold Jeffreys, another statistician who was involved in this case, if there were any other cause that produced a fraction of the deflection effect, he said that would falsify Einstein, which says all of it is due to gravity. Well, so each one of these Newton-saving hypotheses was hit with a kind of a 2-pronged sort of critique. First of all, that the magnitudes that could possibly have been due to the conjecture factor are too small, and if they were large enough to account for the observed effect, other contradictory results, like comets blowing up, would have occurred. Okay. It didn't matter, for example, that people had various personal reasons for hanging on to Newton either, as long as you subjected it to this, like Sir Oliver Lodge believed that he could communicate with his dead son through the Newtonian ether, and so he was very loath to give it up. But the critique, of course, had nothing to do with it. Okay, so these results, or these proposed factors, were considered plausible, but they just were unable to pass severe tests. If you had to save Newton by ignoring the contradictory results or changing the magnitudes of known constants, that would be bad science. So that was the argument. Actually, we didn't get really stringent tests until the 1970s with radio interferometry. These were much better at discriminating. And even then, they couldn't say that all of general relativity had passed severely. But what Eddington did say is that the law is firmly based on experiment, and even if you abandon the theory, this much would be retained. That is, in my wording, the aspects that had passed severely remain through the theory change. Now, Popper, there's a real connection with Popper, general relativity, and severity. Since I'm here, I should mention them. And he's saying what's so special about this prediction, unlike some of the other revolutionary theories of the day, is the risk involved in this prediction. That the theory of relativity is incompatible with certain results that everybody would have expected beforehand. Nobody was expecting them. And this is very different from cases like Freud and Adlerian psychology, where he said any observed behavior could equally well be explained by either of these psychological theories. So this is his famous example that he says leads him to his demarcation. It's just way too flexible. I do modify Popper on a number of core principles in the book. Here, for example, it needn't be the flexibility of the theory, really, but the overall inquiry. Like today, we talk about research and flexibility with cherry picking and optional stopping and so on. The question is, how do you pick up this flexibility, the fact that certain accounts made it too easy to ignore unwanted effects and save the results that you like? They're not really picked up on in logics of induction. And Popper denied that severity, as important as it was, he denied that it can formalize it. Certainly he denied you can formalize it with any of the confirmation logics in the day, that the probability of saving does not capture this idea of the severity of the tests that have been passed. I find it very fascinating to compare the wars between Popper and the logics of induction and today's statistics wars, because they have many parallels. So this is a quote from Alan Musgrave, who's a well-known Popperian, saying, on the logical empiricist view, to come up with a confirmation relation, we only need to consider the statements H and E, H the hypothesis, E the evidence, and we don't have to know which was known first or whether you deliberately proposed H to explain it and so on. That was the idea. That was the holy grail. And there's this analogy here with logics of induction and what I'm calling probabilist account, that really all you need are the hypothesis and the evidence should speak for itself. And this question about flexibility or probing capacity doesn't show up. So in this account, the idea is that the information of the data comes in the likelihood. So this is the probability of the data under H naught, okay, ratio, compared with the probability of the same data under some alternative. Very often likelihoods are misinterpreted, for one thing, because the data are fixed. It's the hypothesis that vary. And as an example of a logic of induction that had been built on this idea, comparative logic of support, you know Ian Hacking, I assume, who's hasn't worked in this area in a while, but he had this idea of the law of likelihood, still popular, that data support one hypothesis, H naught, less well than another, okay, if the first one is less likely in this very technical sense. That is, that it makes the probability of the data less. He rejects his own view not long after. But one of the problems is that any hypothesis that perfectly fits the data is going to be maximally likely. If you find a hypothesis that entails the data, okay, it will get likelihood 1, clearly, very different from probability. George Bernard, who was working in these areas too, said there always is such a rival, namely that things just have to turn out the way they do, perfectly fitting hypothesis. Right? And so Neyman-Pearson introduced the idea of error probabilities because we can't just look at the likelihood ratio. To fix a limit between small and large, we have to know how often such values of the likelihood ratio would occur when we deal with a true hypothesis. Okay, so you see what we're doing is putting a probability on that ratio. The probability that H0 is less well supported than H1, even though, or under the assumption H1 is true, is high for some H1 or other. Okay, that's how they do it. So this is the introduction of error probabilities. So, for example, a well-known example, this is back in Morrison and Hankel's 1970 book, we have 20 sets of differences, and only one of them seems large enough to test at maybe the 0.05 level, then your actual level of significance isn't 5% anymore, it's 64%, or depending on whether you have dependencies or not. It would be the probability of finding at least 1 out of 20. Which is much higher. And this is clearly one of the problems that leads to irreplication. So these are also called spurious p-values. The hunter or the fisher, right, the data dredger, reports these results are impressive. They would be very difficult to achieve under the assumption of H0, when in fact they're very easy to achieve. Okay, so he or she is misreporting the capability of the test. There are many more ways to be wrong with the hunting, and we would give it a concrete specification by saying that the sample space has changed. So you need to adjust the p-values accordingly if they are going to be valid p-values, or at least report the multiple testing occurring. But now we get into some philosophical controversy, because on some accounts of evidence, you never should have had to. You don't need to adjust or report. In fact, they see it as highly problematic. This is something by Stephen Goodman, who's the co-director of this meta research innovation team, saying you shouldn't be adjusting the p-value, adjusting the measure of evidence because of considerations that have nothing to do with the data. Defies common sense. This is a problem. He sees it with the frequentists because they would want to adjust looking at the capability. Yeah? So this formal notion is the likelihood principle. The fact that the evidence just comes in through the likelihood ratio. That's called the likelihood principle. And any account that looks at error probabilities is violating that. And Dennis Lindley, makes it clear: sampling, distribution, significance, levels, power, all of these depend on more than the likelihood function, something that's irrelevant in Bayes' theorem or in Bayesian inference, at least once the data are known, not pre-data, namely the sample space. And also, in this view, like Musgrave had said, it doesn't matter whether the hypothesis was first or second or so on. This is the typical logic of induction idea. So what happens with the reforms? Many of the reforms that are to help get away from replicable results, they obey this likelihood principle. An example would be Bayes factors, and that's like the likelihood ratio, but just the ratio of the posterior probabilities And they say they don't need to know the sampling plan. Jim Berger and Wolpert wrote this whole book called The Likelihood Principle, saying it seems strange that a frequentist needs to know the stopping rule, whether you tried and tried again, you didn't get anything at the first 10, 10 more, and so on. So the error control is lost. Right? And people who endorse these views don't deny it. They admit the error control is lost, but they say they're not interested in error control. So this is Eric John Wanamaker's much. And he's just echoing Edwards, Lemon, and Savage from a long time ago, admitting that if you ignore the sampling plan, you can always reject the null hypothesis, even if it's true. Some people think we ought to then look at the sampling plan. He says, no, this is not the case, and a mathematical analysis can show it. But this mathematical analysis assumes the likelihood principle, assumes that we're going to do evidence by way of a posterior probability, in which case the sampling distribution drops out. So this is what makes today's controversies about replication so fascinating, because of the underlying differences in statistical philosophy. Clearly it's at odds with this famous 21-word solution put out by fraudbusters, Simmons, Nelson, and Simonson, amongst the first ones, who say that the researcher has to delineate how we determine sample size and the data and all of this in the methods section, because the replication researchers find that all of these p-hacking, they coined that term, but it's just the same old data-dependent hypothesis, and stopping rules are really a major source of failed replication. So they put forward this rule. Now, it isn't as if there'd be no other way to block these biasing selection effects, because you could say, well, what we'll do is we don't need those error probabilities because we don't have them in our account, but we could just say these are just too unbelievable, because Bayesians don't have just likelihood, they also have prior. And that would be one way to do it, but there are problems with appealing to the priors to block these inferences based on selection effects. Most notably, it doesn't show what they really did wrong. It becomes a battle of beliefs, and really the data-drenched hypothesis is often very believable. That's what makes them so seductive. And of course, if you do introduce the priors, then you have to get more flexibility. Moreover, what about our central problem of distinguishing the well-testedness of one and the same hypothesis, but two different methods? One, where you have pre-designation and so on. The other, where you have optional stopping and data dredging. Since it's one and the same hypothesis, presumably the prior would be the same, right? And so what we would want to call the distinction by looking at the sampling distribution. And so this would be a problem if you tried to look to the prior. It's okay if you have a question. Okay. Nowadays, most Bayesians don't appeal to subjective priors, but to something called non-subjective priors, or default priors, or reference priors. It's too hard to get subjective priors. The experts don't agree when you try to elicit. And so what are these default priors? They're supposed to prevent beliefs from entering, so they're supposed to be somehow objective. It's unclear how to interpret them. This is why I said at the beginning that the unification, which is supposed to signal the end of foundation, don't work, because there are these questions about how to interpret them. They're not considered expressions of uncertainty, ignorance, or belief. They may not even be probabilities. They're often improper, i.e. they don't sum up to one. So that doesn't seem to be a good way to get around the problem of the data dredging and biasing selection effects. The other thing that happens is that when you try to criticize somebody from data dredging, the whole force of your criticism seems to get lost. You're wanting to downplay the appeal to error probabilities. The researcher who ought to be criticized gets a kind of life raft. Why? Because that critic can say, oh, you're discounting my result by giving a very high prior to the null hypothesis that says no effect. But you can always do that. And the fact that you can always do that means it's not very severe. An example was Darrell Bem. Some people consider this really the start of the replication crisis with Darrell Bem's allegation that he had evidence that people do better than sham at predicting a picture that they're going to be shown in the future. It just so happened it's an erotic picture. But he admits to data dredging. Not only that, he had to look at certain personality features in order to get a subgroup where it really works. Okay? So when he's criticized by Bayesian critics who look at their default prior, giving what we call a lump of prior to the null hypothesis, he just discounts that and says, I know you can always do that. And the fact that there is this huge difference between the p-value and the posterior is called the Lindley-Jeffreys paradox or the Bayes-Fisher disagreement. And so, since you can always do that, I discount it. So this feature, this fact that the p-values can differ from posteriors, is often really at the heart of today's controversies, but they're measuring very different things. So why would you expect them to agree? Actually, there are a large set of cases where they do agree, but very often they don't. We could have a high posterior probability in the null, right? And yet we've got a small p-value which suggests evidence from or incompatibility with the null hypothesis. It might look like the p-value is exaggerating. This is what they always say, the p-value exaggerates. But to the significance tester, the Bayesian is biasing results in favor of the null. And this is Casella and now Roger Berger saying that to concentrate the mass on the point null hypothesis is creating this bias. It also conflicts with the idea that others hold that all of these zero nulls, also called nil nulls, are false. Why are they giving this high spike to it? And there are cases, though, we call them frequentist matching cases, where the p-values can equal the posterior probability, and so there's a lot of latitude there. What happens is that the rival tribes talk past each other on this issue, including issues that lead people to saying that we should redefine significant, make the requirements smaller, and so on. Not all Bayesians accept that view. Some Bayesians reject probabilism altogether. I know that Gelman purports to be, Andrew Gelman at Columbia, purports to be a falsificationist Bayesian, and in something that I consider like a meeting of the minds between Bayesian, Gelman, and this aerostatistician Cosmo Shalizi, they actually say that crucial parts of Bayesian data analysis, especially model checking, can be seen as error probes, in my sense, which he says might be seen to use statistics to implement the Popperian idea. So here we have all of our concepts brought together. Okay. I wanted to say something about a newer approach. I'm prepared to say, in fact, in the last part of my book, I call it probabilist foundations lost, probative foundations found, because the Bayesians also need new foundations, we find. They don't find them in the subjective, and the non-subjective or default Bayesians don't have good foundations. So they could maybe also find them here. But I wanted to say something about this, so if I can go a little more. This new idea that of the diagnostic screening model, which just takes us right back to Iron-Eating, where he says if we imagine randomly selecting hypotheses from urns, 90% of which are true, consider just two possibilities, zero effect and a meaningful effect, everything else is ignored. Take the prevalence of 90% as giving you the priors. So this is the null that's getting a high prior. Then you go ahead and reject, the way he makes file, with just a single 0.05 significant result. Then you can get most findings are false. I don't know if you can see that little urn. Okay. I mean, there are a lot of issues about this. What he's saying is that this is really the prevalence of true nulls given the test rejects a null can be highish, greater than 0.5, even though we have this error probability, which is 0.05. Again, it's really pointing up a difference, and it's transposing the conditional, okay? And there's no reason to suppose that the type 1 error probability would equal to this. I call that the false finding rate. Okay, so that's what's going on there. But, so where they see it as a major criticism of tests, there are these confusions because it's not really a type 1 error. And the other thing is it seems to have kind of a little bit of the worst of both worlds, a crude performance ideal with a probabilist assignment. So it's not really true to Bayesian or to frequentive. And of course it might work in some screening ideas. So here's the way that the components from the ordinary Neyman-Pearson test are used here as kind of likelihood. So you might want to take a look at this and you have a chance and see some issues that arise of the false finding rate and the complement, the posterior predictive value. And the result of this is that the higher the power against a claim, the more evidence for that claim, which really is the reverse of what happens in Neyman-Pearson test. So you get some very strange results. But I wanted to ask you what you think about getting this prior via the prevalence. And first of all, what is it? You might know Hoku, who's here at UCL. He calls it the proportion of experiments that you do over a lifetime in which there's a real effect, or proportion of true relation. I can't imagine what we would use for the prevalence of general relativity hypothesis in 1919, that experiments could be individuated in all kinds of different ways. So getting this prevalence rate doesn't seem to work. But also there's this fallacy going on in imagining that the hypothesis that I draw from an urn, even if we imagine that the hypothesis I'm about to study is randomly selected from an urn, and even if we imagine that 90% of those are no effect, okay, it wouldn't give the probability of 0.9 to my particular hypothesis, right? That's just like a fallacy when you assign a probability to a particular confidence interval, when really all you know are the rates. And the other thing is that the zero effect, meaningful effect, are non-exhaustive. You shouldn't be using up all your prior on that. But this is a popular account. I think also, do we want this? We want this high posterior predictive value. Paul Meehl always warned us that all nulls are false because, at least in the social sciences, we have what he called the crud factor, where everything's related to everything. And so you could get a high prevalence this way, but I don't think that would mean that we have a good replicable hypothesis. On the other hand, in fields where prevalence is low, because maybe they hold off quite a bit before they put forward a hypothesis, like the general relativity or the Higgs or something, that actually is going to give you a much more replicable hypothesis. What's doing the work has nothing to do with prevalence. It's this severe probing, triangulating with other measures, and so on. So that's a popular account that I should throw out there. I call it the diagnostic screening model because it's something that comes from diagnostic screening in medicine. A lot of people don't like it in medicine either. And Ioannidis says, in a sense, stay safe. We should look at research questions where the pre-study probability is already considerably high, because then, if we get a significant finding, we'll get a high posterior prevalence. That's not at all what we want when we say that we're looking for novelty, right? We're going to stick with some very boring, non-challenging hypothesis to satisfy them. Okay, now I will just say one word if I could go further, because I'm certainly not endorsing tests as they're usually used. I have already reformulated tests long ago, and the reformulation in which what you're going to do is evaluate the severity of a certain claim in relation to a test and data. Okay. The reformulation builds on a discrepancy gamma from some reference hypothesis. So instead of a binary cutoff, the particular outcome is used to infer discrepancies that are not warranted, and it's an important part of the inference to say which ones are poorly warranted. And this could be developed in either a sort of Fisherian fashion or Neyman-Pearson fashion. Well, I first did it in Neyman-Pearson fashion, but working with David Cox, we developed this frequentist principle of evidence that would allow you to do it in a Fisherian mode. And so just to consider one example, because many people these days are saying, you know, failing to reject a hypothesis is just completely uninformative, and of course lack of replication is failing to reject. Are we really going to say they're uninformative? Well, no. In a case where you don't reject the null hypothesis, we call those moderate p-values. In other words, non-statistically significant result. We might be able to set an upper bound if we find there's a high probability that you would have gotten a larger difference, or this is a case of inferring a mean. If the mean were greater than mu1, and very probably you would have gotten a larger difference, then you're not getting the difference, is a good indication that the mean is not that big. However, if you had very little chance of detecting the difference, even if it's there, then not finding it is poor evidence. Okay. So this is how you deal with negative results. Positive results is analogous, and just to give you that idea. And I'm going to stop in order to have questions.